And we're back talking about kinematics, and today we're learning about vector addition. Vectors. The simplest vector for us to talk about for now is displacement. We'll get into more complex vectors like velocity and forces later on. So we're talking about displacement, and vectors have two parts. Part of it is the magnitude. So if we're talking about displacement, magnitude is the numerical value. Could be 100 meters. Okay, that's an example of the magnitude of your displacement. Another part of vector is that it has to have direction. The direction, there's a few different ways you could describe direction. You could say north, south, east, west, so you're using cardinal directions. You could talk about a coordinate plane or a coordinate axis where you have positive, negative x, positive, negative y, positive, negative z. Or we can use angles. So today we're going to talk about angles. So if we're talking about displacement, the displacement, it's always in a straight line. All vectors are always in straight lines. They have one direction. Get your one direction jokes out now. Come on, say it. Haha, one direction. Get it out now so I don't have to hear it in class. One direction. You could say I ran 100 meters north. Magnitude of 100 meters, direction's north. I ran 100 meters in the positive x direction. Magnitude 100 meters, positive x direction is your direction. Or I ran 100 meters at 45 degrees. 100 meters is magnitude, 45 degrees is your direction. If you're using a coordinate axis, here are the different types of positive and negative x, positive and negative y you could see. We won't be doing a whole lot of positive, negative z in this class, at least not for now. If we're using degrees, you can use north, east, south, west here, or positive, negative x, positive, negative y. If you're moved at a direction of 45 degrees, that's a positive 45 degrees from east. So in physics class, we always think of east as being 0 degrees, and positive is counterclockwise to that. I think if you use a compass, 0 degrees is north. In physics class, we're going to do it a little differently. East is 0 degrees, and positive is counterclockwise than that. So here's positive 45 degrees. Here would be positive 135 degrees. Again, you're going from the east. Here's positive 225 degrees. And here's positive 315 degrees. If positive degrees are counterclockwise, then negative degrees could be clockwise. So here you see positive 315 degrees, go all the way around there. That's the same as negative 45 degrees if we're going from the bottom here. Remember, full circle is 360 degrees. As a rule of thumb, if it's in the first, second, or third quadrant, typically we'll use positive degrees if we're talking, and that'll be counterclockwise. If it's in the fourth quadrant, you might use negative degrees or counterclockwise or clockwise. All right, let's get into adding displacement vectors. Knowing what a vector is important. Adding it's where they really become useful. It's kind of like drawing a treasure map. You start here, you walk 20 paces towards the mailbox, walk 35 paces towards the oak tree, and then walk 12 paces north, look for the X on the ground. X marks the spot, right? When you add vectors, very important here that you add tip to tail. So notice that the tip of this vector here matches up with the tail of this vector right here. Same thing over here. Tip of this vector matches up with the tail of that vector. Vectors are always added, always, always, always tip to tail. When you add numbers, the answer to that is the sum. So the sum of adding vectors is called the resultant vector. And the resultant vector is the straight line vector from where you started to where you finished. Sometimes we call that capital R for resultant vector. So this resultant vector is not a tip to tail vector. All the vectors you added together, those ones in green here, those are added tip to tail. And this red vector, the resultant vector, is from the start straight to the finish. Okay? That's as the crow flies when we were talking about displacement. Maybe you remember that story from class. We can name vectors A, B, and C here, and the resultant vector would be A plus B plus C would equal R, your resultant vector there. Let's add some vectors on just the x-axis, so vectors in one dimension. Let's say that you moved 20 meters in the positive x direction. That would look like this, 20 meters in the positive x direction. Then you move 8 meters in the negative x direction. So 8 meters in the negative x direction. Add our vectors tip to tail. You're going to draw the first vector, and then from the tip of that vector, start with the tail and draw your next vector. The resultant vector is from where you started straight to where you finished. So in this case, our resultant vector would look like that, and it would be a positive 12 meters there. So if we were to do this, if this is displacement, the resultant vector is just a positive 12 meters from the start to the finish. I believe that's the first example on your notes. Make sure this gets written down, and then you can try and attempt those other 3 examples and compare them with your classmates when you get back to class. Now, what if they're in different axes? What if they're going in different directions? The first one, the example we just did, this was of an example when everything was moving in the horizontal axis. What if they're moving in different directions, different axes, different dimensions? So here's an example. What if we move 20 meters in the positive x direction, but then move 10 meters in the positive y direction? What's going to happen here? The resultant vector is from where we started, right here, where we started straight to where we finished. How far is this? What's the length or magnitude of this resultant vector, and what direction is it going in? Yeah, you guessed it. Maybe you see it here. This is a right triangle. We're going to use the Pythagorean theorem, and we're going to use all of our sine, cosine, and tangent functions. Ah, joy, right? I'll just show you the work here. We'll do this more by hand in class, but the length of this resultant vector, or the magnitude of the resultant vector, you're going to use the Pythagorean theorem. 10 squared plus 20 squared would be this resultant squared. You should find the resultant to be 22.4 meters. Similarly, we can use some trig here. We want to figure out what direction is this moving in. The opposite side is 10. The adjacent side is 20. We can use inverse tangent to find that this is at an angle of 26.6 degrees. Very important, guys, especially if you're in a pre-calculus class or calculus class. You do a lot of work in radians. Make sure that your graphing calculator is set to degrees, okay? That would make for some very incorrect answers and very frustrated you. All right, again, I think this is the first example on this part of your notes. The other 3 are for you to try out. Make sure you're using Pythagorean theorem, the inverse tangent function to find that angle. Compare those with your classmates to see if you guys get it or not. Now, what if they're both at angles? In the previous example, they were in the x direction and the y direction. What if they're at weird angles? So say you move 20 meters at 45 degrees, and then you move 10 meters at 30 degrees. Well, we can add these in the same way. There's extra steps, but the overall pattern here, the overall steps are the same. We're going to add these vectors tip to tail. So we've got our positive 20 meters at 45 degrees. We'll draw that vector. Then we're going to draw our next vector, positive 10 meters at 30 degrees. Notice how these are drawn tip to tail, always tip to tail. The resultant vector is from where you started and drawn directly to where you ended. If we drew these to scale and we used rulers and protractors, you could do it. You could measure this length, measure this angle. Unfortunately, during the AP test, they don't allow you to use a ruler and a protractor, and it turns out that that's a very long-winded way to find an answer. We can use some math to our advantage here. What we're going to do is we're going to find components. Notice here I've got the x and y components drawn for the blue vector and for the green vector. Our first job is going to be to find these x components. Here is your equation, if this is your vector, to find that x component. I'm using the cosine function here. I can show you in class how this is done. The x component is the adjacent component vector. And so we can take the length of this vector here, the magnitude, multiply that by the cosine of the angle, and we get the x component. So for your green vector here, that x component is 8.66. And for the blue vector, that x component is 14.14. So I'm going to write those down. Make sure you get this equation down in your notes. After we find the x components, we want to find the y components. Notice I've got the x components drawn on there for us so we don't forget them. The y component, that's the opposite side to this triangle here. If we're finding this y component, we can use the sine function and the magnitude of our vector to find the y component. You're maybe wondering, why is this useful? Why do I need to know this? We're getting there, okay? Take it in bits and pieces. Green vector here, y component is 5. Blue vector here, the y component again is 14.14. So we've got these vectors. The question is the resultant vector of these components when they're added the same as the resultant vector of our original blue and green vectors? And the answer is yes. We have these components here. If we add all these up tip to tail, the same resultant vector. And here's why this is useful. We can rearrange these so that we have one big x component, one big y component. Right? Here's what this looks like. We're going to add these x components together to get one x component for our resultant vector. We're going to add the y components together to get one component for our resultant vector. And we end up with this. A simplified triangle of all the motion in the x direction, all the motion in the y direction, a simple right triangle so that we can use the Pythagorean theorem again to find the resultant vector, and use the inverse tangent again to find the angle. Here's that work done out for you. I'll give you a second to write that down. Maybe you want to pause the video. We found the horizontal components, the vertical components, added the horizontal, added the vertical, and now we can use those to find the resultant vector's magnitude and the angle at which it's moving. Kind of a recap of that. This is what we just did. Found the x components, added them together to make the x component of the resultant vector. We found the y components, added them together to find the y component of the resultant vector. We used the Pythagorean theorem of those x and y components to find the magnitude of vector r, the resultant vector. Then we used the arctangent or the inverse tangent of those x and y components to find the direction of vector r. Very important that you understand the steps we took there. Tips for more advanced problems: draw a picture. Pictures really do help. Pay attention to all the angles and directions that are happening. Draw a picture. Label all the angles and directions. Draw a picture. Label the components and the directions. Draw a picture. Often drawing a picture is the key to success in physics. Whether it's drawing vectors or we're doing free-fall problems, pictures help. They help you visualize what is going on. So I hope that helped. A little bit of vector addition there. There's some extra practice at the end of the note sheet. When we come into class, we're going to see how this really applies to a physics class. But my hope is that you have some basic understanding of finding components, making sure all the components are in the right direction, adding those together, using the Pythagorean theorem, using the tangent function, and I guess I'll find out what you know when we get back in class on the next day. Have a good one, guys. See you later.